In this video, we're going to continue practicing with the rules of logarithms to answer some additional questions. In the first two examples, the instructions are to write each expression as a single logarithm with a coefficient of 1. We're going to assume that all variables represent positive real numbers where a is not 1 and b is not 1 either. Basically, we're going to apply the same properties that we practiced with in the previous video, but in reverse order. In the first example, we have logarithm base 4 of x minus logarithm base 4 of y plus logarithm base 4 of z. It's always important that when we apply these rules that we confirm that we're working with logarithms that have exactly the same base. Otherwise, the terms have to remain separate. Using the product and quotient rules, we can write this as logarithm base 4 of x times z, because those logarithms have positive signs in front of them, divided by y, because that logarithm has a negative sign in front of it. You can also enclose this in parentheses for clarity. If you're a little confused as to why this is true, try just rearranging the terms so that the positive logarithms are first and the negative logarithm is at the end. Maybe it'll be more clear here that these two logarithms, when combined by the product rule, will result in x times z as your argument, and then using the quotient rule for the last term, the argument is divided by y. In the second example, we have the natural logarithm of x minus 2 times, and here we have a longer expression, natural logarithm of x minus 8 plus the natural logarithm of x plus 8. Here, because we have these brackets enclosing the last two terms, that operation must be done first before multiplying by 2 and before subtracting from the natural logarithm of x. So we want to follow the order of operations. So let's write this as natural logarithm of x minus 2 times. Here we have addition, so we're going to take the natural logarithm of x minus 8 times x plus 8. Next, we're going to deal with this 2 coefficient. Using the power rule, we can write this as natural logarithm of x minus the natural logarithm of, and here we can actually go ahead and multiply x minus 8 times x plus 8 and write it as x squared minus 64. And that 2 in the front as a coefficient can come up and become the exponent on the argument. Finally, we can apply the quotient rule to deal with this subtraction. And using the quotient rule, we can write this as the natural logarithm of x divided by x squared minus 64 quantity squared. For clarity, if you want, you can enclose this into some grouping symbols. Next, let's look at the principle of logarithmic equality, which states that for any logarithmic base a and for any x where y is also greater than 0, these two statements are equivalent. X is equal to y, and logarithm base a of x is equal to logarithm base a of y. In other words, two expressions are equal if and only if the logarithms of those expressions are also equal. I may add that these logarithms must have exactly the same base. So in other words, if two logarithms are equal and their bases are equal, then their arguments or results must also be equal. Let's use this principle to work on these next 4 examples. First, we have logarithm base 4 of 3x plus 1 is equal to logarithm base 4 of 13. The logarithms are equal with equal bases, therefore their arguments must also be equal. This gives us the linear equation 3x plus 1 is equal to 13. Solving for x, we get that x is equal to 4. Next, we have common logarithm of 32 plus common logarithm of 2 is equal to 2 times the common logarithm of x plus 2. Remember that when I'm using the phrase common logarithm, I'm referring to a logarithm with a base of 10. On the left-hand side, we're going to use the product rule to write this as the common logarithm of 32 times 2. On the right, we'll use the power rule to write this as the logarithm of x plus 2 quantity squared. On the left-hand side, we have the common logarithm of 64, and on the right, we have the common logarithm of x plus 2 quantity squared. These two logarithms are equal with equal bases, therefore their arguments must be equal. So we'll say that 64 is equal to x plus 2 quantity squared. Using the square root property and interchanging the two sides, we can say that x plus 2 must equal plus or minus the square root of 64, or that x plus 2 must equal plus or minus 8. Subtracting 2 from both sides, we get that x is equal to negative 2 plus or minus 8, which gives us two values for x. Either x is negative 2 minus 8, or negative 10, or x is equal to negative 2 plus 8, which will give us 6. In the next example, we have natural logarithm of 4 plus the natural logarithm of x. And I want to remind you that when I use the phrase natural logarithm, this is a logarithm with the base e, where e is a fixed number called the Euler constant, or the natural number, with an approximate value of 2.71. On the right-hand side, we have natural logarithm of 5 plus the natural logarithm of 2x minus 3. We're going to use the product rule on both sides. On the left, we'll write this as the natural logarithm of 4 times x. On the right, we have the natural logarithm of 5 times 2x minus 3. The two logarithms are equal and they have equal bases, therefore their arguments must be equal. So now we solve the linear equation, and we get that negative 6x is equal to negative 15, or that x is equal to negative 15 over 6, which reduces to negative 5 halves. In example 4, we have logarithm base 7 of x plus 3 plus logarithm base 7 of x minus 2 is equal to logarithm base 7 of 2x plus 14. Note here that we're going to use the product rule to write this as logarithm base 7 of x plus 3 times x minus 2, and on the right, no change is necessary. So we have two logarithms that are equal with equal bases, therefore their arguments must be equal. I'll go ahead and set x plus 3 times x minus 2 equal to 2x plus 14, and distributing, we get x squared plus x minus 6 is equal to 2x plus 14. Looks like we have a quadratic equation, so let's clear one side. We have x squared minus x minus 20 equals 0. So we have x minus 5 times x plus 4 equals 0. So we have x minus 5 equals 0, or x plus 4 equals 0. And this gives us two possible solutions for x. X is 5, or x is equal to negative 4. At this point, I want to pause and look at examples 3 and 4, the two that we just worked out, because I do see that we have a situation here with number 4 and that I actually made a sign mistake on number 3. On number 3, negative 15 should have been divided by negative 6. That was my bad. So that actually will give us a positive 5 over 2 as a result. I'm going to go ahead and fix that. But for number 4, what caught my eye is I think I have a problem here with one of these supposed solutions. One of them just isn't going to work. Remember that the argument of a logarithm must be positive. The argument cannot be negative or 0. I think that we have a troublemaker here. If x were to equal negative 4, look at what happened to this argument. The argument would be negative 1. That's a problem. This argument would have been negative 6. So x cannot equal negative 4 because it violates a restriction.